Hi everybody. In this video, we're going to go a little bit more in depth with the position versus time and the velocity versus time graphs. If you haven't watched the previous video, please make sure that you do. It is the introduction to the position versus time and velocity versus time. We are going to build upon that knowledge so that you can have a better understanding of what different kinds of problems you might come across when looking at these position versus time and velocity versus time videos. Alright, so when we go over these graphs, please make sure that with every new graph, you take the time to stop, pause the video, and sketch out the graph so that you can follow along with everything that I write. Alright, so the first graph that we're going to look at is a position versus time graph. Now, as a reminder, remember, graphs in physics will always be in the y versus x fashion. So this is the y-axis, which is position, and t, or time, is the x-axis. Alright? Now, we have two lines. We have line A and we have line B. So these are two objects, object A and object B. And both objects are moving, and with that data, we were able to create this graph. So let's do a quick review on all the things that we can figure out from this graph. So let's take a look at graph A. So before I go into any of the more in-depth stuff, let's do a quick reminder. Alright, so for a position versus time graph, remember that the slope represents the velocity, okay? And we can take a look at the points on the graph. Alright, so if we were to take a look at line A, we can see one that is a constant slope, so it's not speeding up or slowing down. The velocity is constant. And in order to find the slope for line A, so I'm going to do A here. Remember, slope is the change in the rise, or the y-axis, over the change in the run, or the x-axis. Okay, and this will give us our slope. So what I like to do, and I do recommend that you do this, is whenever you find slope, if you have something linear like this, definitely look for points that intersect the crosshairs. So for example, I'm going to choose this point right there. And another point is right up here. Now, I know that I could choose 0, 0, but that just makes the math a little bit easier, but that's not always going to be the case here. So let's label these points. We see that this one is 2 seconds versus 4 meters. Okay, so those are my coordinates. And here I have 4 seconds versus 8 meters. Right? Once again, those are my two coordinates. All right, now let's figure out the slope. For the delta y versus delta x, I'm going to rewrite that because our delta y is actually the change in position. So delta x over delta t. Okay. Now, kind of looks like I just swapped this delta x here, but remember this is representing the x-axis, not the variable. All right, so the change in x is x final minus x initial over t final minus t initial, just like that. So the final position is 8 meters, minus your initial position, which is 4 meters, over your final time, which was 4 seconds, over your initial time, which was 2 seconds. I'm going to add my units up there. So when I do this, I get 4 meters over 2 seconds. All right, and this gives us a total of 2 meters per second. All right, so for object A had a velocity of 2 meters per second. All right, before I go into object B, let's pause. Let's think about this before we actually analyze this. This is something that you might be asked to do when you're not necessarily given numerical values, but you got to take a look at these things qualitatively. So if I were to ask you, if this is object A, and you know object A has a velocity of 2 meters per second, what about object B? Do you think it's going faster or slower? Okay, so there's a couple of key things here. If I'm asking you if it's going faster or slower, I'm asking you about the velocity slash speed. In this case, it'll be velocity. So if I'm asking you, is it going faster or slower? Ask yourself, if it's velocity, what about a position versus time graph tells me about velocity? And of course, the answer, as we discussed, is right here. It's the slope. So let's take a look at object B's slope. Does this slope look more or less slopey, quote unquote slopey, than object A? Now when I say slopey, what I mean is if it's not slopey, it's like flat, it's horizontal. But if it's very slopey, it's more vertical. So object B, if we take a look here compared to object A, object B is going more towards the flatter slope. So it's not as quote unquote slopey. So what that means, it has a smaller slope. Smaller slope, smaller velocity. So let's see if that's true. Let's do object B. Remember, the first step is to always choose 2 points on the graph, and those 2 points can help you find the slope. I'm going to choose this point right there and that point right there. Okay. I'm going to label those points with the coordinates. So we have 4 seconds and looks like 4 meters. And for this one, it looks like we have 2 seconds and we have 2 meters. All right. I'm going to just jump from this equation down here. So we have delta x over delta t is equal to x final minus x initial. Notice how what I'm doing is I'm writing out the equation because it's just very good practice. Okay, 4 meters is the initial or the final position. 2 meters is the initial position over 4 seconds for the initial or the final time, and 2 seconds, which is the initial time. So we get 2 meters over 2 seconds, and that simplifies itself to 1 meter per second. So this is object B's velocity. So if we were to compare object A versus object B, you tell me, were we correct? Is object B slower than object A? And I would say yes. Yes, it is, because 2, the magnitude of 2 is greater than the magnitude of 1. All right? We have another graph here. Once again, take the time to pause the video and sketch out this graph with all relevant parts. Let's keep things the same. I'm going to make this line A, and we'll make this blue one B. Okay, so here we have 2 objects, A and B, and now I threw in you for a little loop. Things are slightly different here. For the first time, we see a line with negative slope. It's going in the downward direction. Now, let's do a quick reminder. Remember, in physics, the negative number or negative anything in front of a magnitude or in front of a number just represents the direction. It doesn't mean that it's small. Okay, a lot of students like to compare negative with small, and that is not the case. It's just the direction. Now, to keep things simple for us, I actually saved the line from before. So this is the same line from the previous problem, and we know that for A, the velocity for A was 2 meters per second. Okay. Now let's see what it is for B. Now before we start, I do want to take the time here to point out one very important part, and that's up here. Okay. So notice that this line, it doesn't start at 0, 0. This line actually starts at 0 seconds. This line starts at 6 meters. So if this were a real life scenario and we have a object at position 0, what this object is doing is starting in front of object A, okay? And time occurs and things happen that gives us this graph. And we'll go into it after we figure out the different parts. So once again, we're going to find the velocity of B. Okay, remember, velocity is the change in position over the change in time. Now luckily for us, this equation is the slope. So this is position final minus position initial over time final minus time initial. Before I do that, I'm going to find the 2 points that we can use. You know what? Let's keep things simple. I'm going to use this point over here, 0 seconds, 6 meters, and this point right here, which is 2 seconds at 0 meters. All right. Now, for those of you that are following at home, I'm going to point out a couple of things where you should be very careful. The final position here is 0 meters minus the initial position, which is 6 meters. Okay. Now the signs here is very important because sometimes this 6, it could have been a negative 6, and that'll give us positive numbers. Anyways, just be very careful with that and where you put the final and the initials. The final time is 2 seconds minus the initial time, which was 0 seconds. All right. So if we do that math, we get negative 6 meters over 2 seconds, which gives us negative 3 meters per second. All right. So this tells us a lot of things. If I were to ask you, according to this graph and according to our math, which object was faster? Okay, a lot of students will say object A was a lot faster, Mr. Lee, but that's not the case because we only care about the magnitude or the number. So let's start off by writing that velocity A is less than velocity B. Okay, and that is because velocity B has a speed of 3 meters per second, but it's going in the negative direction. Object A has a velocity of 2 meters per second, but it's just going the positive direction. And so what that means is that the 2 objects are just approaching each other. Okay, and we can see that here in this graph. So a common question that you would get is, when do these 2 objects meet? And we can tell visually that the objects meet at a very specific position, and that position is right here. So it looks like they meet right there, okay, whatever that position is, okay, and they meet at exactly right around whatever that time might be, okay. So at this location and at this moment of time, two objects, they meet and they go past each other. Is that cool? All right, we'll do one more. All right, I am here to throw you in for a little bit of a loop. We did position versus time graphs. Now we're doing a velocity time graph. Once again, pause the video and sketch this down. We have here a piecewise function. We have a horizontal line up there at the 4, and then a horizontal line at the -2. All right. So this is a velocity versus time graph. Let's do a quick reminder. For a velocity versus time graph, the area under the curve, it represents the displacement. So in this video, we are going to see if this was the velocity time graph for an object, exactly what happened. You know, how far or what is the total displacement for this object? You know, assuming that the object started at initial position of 0. So if this is the area under the curve, let me give you a couple of tips that I know really helped me. So let's call this the first part of the trip, part A, and down here is the second part of the trip. We know that in part A, I'm going to jot down a couple of things. The object had a constant velocity, and we know it's velocity because that's the y-axis. The object had a constant velocity of 4 meters per second. Okay, and it looks like the object traveled for a total of 3 seconds. All right. So the question is exactly how far, or what was the object's displacement during trip A? Okay, so in order to do this, what you can do is you can use the formula. Velocity is displacement over time. Okay, and we could just plug it in. But if you're given a graph, I want you to get into the habit of using these tools for graphical analysis. So in order to find the displacement here, we need to isolate that value. So it'll be delta x is equal to velocity times delta t. And we got that by multiplying both sides by delta t. Okay. And when I do that, the numerator and the denominator, they cancel out, leaving us with this equation down below. Now, if we are multiplying the y-axis by the x-axis, okay, whenever you multiply the y and the x in the original equation, graphically, that is represented as the area under the curve. So first off, let's identify this curve. Okay, let's shade it in gray. This curve is right here. It's that thin blue line up there. So the area under that curve, let's do it in, yeah, let's do that. Let's make it nice and big. Is this entire region right there. Try not to mess up. This entire region, this giant rectangle, is the area under the curve. Notice, I only went up to the 0 mark when I did my shading. Okay, so this shape, this rectangle, represents the displacement from 0 to 3 seconds. So if we were to figure that out, we would say that the delta x is the change in the y, so that is from 0 to 4, times the x, which is from 0 to 3. So 4 times 3 gives us a total of 12 meters for our displacement. Okay, so that's the displacement for trip A. Now for trip B, that does change slightly. Let me show you how. So for trip B, we are going to be looking from 3 seconds, okay, because that's when trip B starts, all the way up until 6 seconds, because that's when the trip ends. Okay, and this thin blue line down here, that represents the object's velocity. So for trip B, the object had a velocity of, what was it, -2 meters per second. The time frame, the delta t, it went from t final minus t initial, so that was 6 seconds minus 3 seconds. So the total elapsed time was, what was that, 3 seconds, right? And the area under the curve, I'm going to do this in green. The area under the curve is represented from the line to the 0. Okay, and that's a thing that a lot of students miss. It's from the line to the 0, even if it's in the negative region. Okay, so I'm trying to shade that without going over a lot of the important pieces of information there. All right. So if I were to ask you, find the displacement of trip B, we can say that displacement is equal to velocity times the change in time. And we know that the velocity was the y-axis, which is -2. And the change in time, we went from 3 seconds to 6 seconds. And so we can say t final minus t initial, which is -2 times 6 seconds minus 3 seconds. For -2 times 3, that gives us -6 meters. Okay. Now remember, this negative, it doesn't mean that it's small. It just means that it's going in the reverse, or it was a reversal of the displacement. Okay, it's just a direction. All right. So in trip A, this object traveled for a total of 12 meters. That was the displacement. And for trip B, the displacement was -6 meters. So if I were to ask you, what is the total displacement? All we would have to do is add up these two numbers. Would be 12 minus the 6. So this object had a total displacement of 6 meters. Okay. Area under the curve and slope, we will be going over that a lot more. But tune in next time, we're going to add acceleration to the mix. I'll see you then. Bye-bye.